Good morning, students. Here in Bengaluru, the weather is very bad. It has been raining since morning because of the cyclone. So I was waiting for some students to join such that they will not miss out. But anyhow, we cannot wait anymore. At least there are 9 students now. Let us start the class. So today's class is common source amplifier and common drain amplifier, its simulation and its layout. Both of these experiments will not be over in one class. So today we will be discussing only the common source amplifier. In the next class, we will discuss the common drain amplifier. Now to tell you one more thing, you have one more theory course in the next semester that is called as microelectronic circuits. In the 5th semester, you are now studying Cmos Vlsi design, that is the fundamentals of Cmos Vlsi and the construction of digital circuits using Mosfets and its fabrication part also. The analog design using Mosfets is going to be covered in the next semester in another course called microelectronic circuits. So this common source and common drain amplifier circuits are not present in your theory course in the 5th semester. But we thought that anyhow it is a VLSI lab now, let us cover these experiments now in the 5th semester. Its theory can be dealt with in more detail in the next semester. In general, whether to have practicals first, then theory next, or whether to have theory first or practicals next, that does not work out in any way. Sometimes they must be together. Sometimes practicals will give you some hands-on experience, but its theory will become much bigger. For example, the transmission gate itself is a very small experiment, but if you get into the theory of the transmission gate, it is a much bigger topic as such. So we thought, let us introduce these amplifiers to you in this semester and let its theory part be dealt with in the next semester in detail. But whatever is the theory part required for conducting this experiment, that we will be dealing with in the lab class itself. That was one thing. Another thing is, for your seniors in the 5th semester, there used to be 3 labs. One was analog communication lab, and one was microcontroller lab, and one was VLSI lab. And in the 6th semester, they had 2 labs called advanced communication lab and embedded system design lab. For your scheme, for the 175 credit scheme, we made a change in the curriculum in such a way that now in the 5th semester, you have only 2 labs. One is microprocessors lab. We changed the microcontroller course into a microprocessor content itself. So it is a microprocessor lab. Then VLSI lab anyhow you have. Instead of the analog communication lab, in the next semester, we have clubbed the analog and digital communications together, and that is called as communication lab. And you will again have embedded system design lab in the next semester. So that way, some of the theories which you learn in analog communication, the experiments will be conducted the next semester in the communication lab. Otherwise, earlier your seniors were having a burden, especially in the 5th semester, where they were slightly more loaded. They used to have 3 labs and the mini project. Of course, that was for the 200 credits. Now it is for 175 credits. We thought we will reduce it. So that is how the theory portion of analog communication, its lab portion will be conducted in the next semester. Now the theory portion of common source common drain amplifiers or op-amp or later on R2 RDAC, they are all going to be covered. Differential amplifier, they are going to be covered in the next semester in the microelectronic circuits. Its lab portion is going to be covered now itself. So to some extent, we have made these minor changes. Now with this brief introduction, let me start today's lab class. Let me write a circuit now. Now this is a primitive BJT amplifier. This is a primitive BJT amplifier where you can see a DC blocking capacitor at the input and a AC coupling capacitor at the output. Then you can see a regular fixed bias circuit. I have written a primitive BJT amplifier, which is a regular fixed bias amplifier. Now you already know what for these components are required. At the input, the capacitance is required because there is a DC biasing of the base here. So we need one RB here. We need one base resistance. Then at the collector, we need one collector resistance, because when the transistor switches on, the power supply should not be shorted to ground. That is why we need a collector resistance. And then we need a AC coupling capacitance at the output, because the transistor is a DC device. Even at the input, as it is a DC device, we need a DC blocking capacitor. So when you feed the input signal here, it will get amplified at the output and you will get a 180-degree phase shifted output. I am revising your BJT basics. Now if I have to replace the same thing with the MOSFET, let us say I replace the same thing with the MOSFET. I have written, instead of RC, I have written RD. At the drain, there is a resistance. Then we need a coupling capacitance at the output. We have connected a Pmos device now. Now, again at the input, we will give the input signal like this, and we want an output signal at the output. Now the point is, at the output, just like RC, you need RD. Because when the transistor goes into complete linear region, in the case of MOSFET, then power supply should not be shorted to ground. And at the output anyhow, we need a coupling capacitance. What about the input? Do we require a resistor to the gate? Just like we have a RB here, do we require a resistor to the gate? That is my question. Can anybody answer?
I don't think so, sir.
Yeah. So why not? Why not? The answer is BJT is a current control device and it has a factor called beta. Whereas MOSFET is a voltage control device and it has a factor called GM, transconductance. So the MOSFET does not require any gate current at all, whereas the BJT required a base current there. As the MOSFET does not require any gate current, no need of biasing the MOSFET that way. That is one reason we don't require a gate resistance. Next, do we require this input coupling capacitor there here at the gate of the MOSFET? Any answer? We have this DC blocking capacitance at the input. Do we require that capacitance here also? Answer is no. We can directly connect the input. Reason is already there's a capacitance at the MOSFET itself. You can see it is called metal oxide semiconductor. Means there is a oxide layer in between gate and the channel. When there is already a gate capacitance, why do we need one more capacitance for blocking DC? So we can directly give AC as input to the MOSFET. Of course, at the output we require these two. So you can compare these two circuits now. The circuit with BJT requires two more components, where the circuit with the MOSFET requires lesser components. That I am comparing only with the fixed bias. Now that is the advantage of MOSFET. But the disadvantage of MOSFET is that the way in which BJT gives voltage gain, the same amount of gain is not possible with MOSFET. Now that is the compromise which we are making when we choose MOSFET for amplifiers. Now the circuit which you see at the left side is called common emitter amplifier because the emitter is common to input and output. Input is given at the base, output is taken at the collector. In the same fashion, at the right side, you have this common source amplifier, which means input is given to the gate, output is taken at the drain, source is common to input and output. That is what? This is now common source amplifier. Now let me clear the screen and let me write one more circuit only with the MOSFET. Or let me go down to the circuit of common source amplifier. Now let me ask you. Now what difference do you see here? I had written a circuit there at the top with the resistor at the drain of the MOSFET. Now I will zoom this circuit. You can see this circuit now. Now instead of the resistor, you are seeing a transistor at the top. And below you are seeing the regular amplifier transistor. This N MOSFET is basically a amplifier transistor where you have input and at the drain there is output. Input is given at the gate. What difference do you see when you compare this circuit with the circuit which I had written earlier? One difference obviously is the resistor is replaced with the Pmos. I will come to that later. Now the resistor is replaced with the Pmos. This I will come to that later. But do you see any other difference here? Any answers?
Difference or similarities with another circuit?
Difference.
Between the previously drawn one and this one.
Yeah. Okay, let me tell you the answer. You are seeing VSS instead of ground. In the circuit which I wrote earlier, source was connected to ground. Here the source is connected to VSS. Now can anybody tell me what is the difference between VSS and ground? Similarly,
Zero potential.
yeah?
Ground is zero potential. VSS, no. Source potential, I think.
Yeah, VSS is connected to source here. Ground is 0 volts, but VSS, it is connected to source. So can it be different from 0 volts? Let me help you. Ground is 0 potential, VSS is minus VDD. Okay, Kuldeep has given this answer. Fine. In general, we take ground as 0 volts only. But when we take VSS, it need not be ground. For example, let me write. Let us say VDD is 2.5 volts. Let me change the color. Let us say VDD is 2.5 volts. Now VDD is 2.5 volts. VSS is now minus 2.5 volts. You would have used such VCC and VEE when you worked with op-amps. Operational amplifiers can be used with the single supply also. They can be used with the dual supply also. Now what is the advantage of using the dual supply when compared to the single supply? Now in the case of a single supply, your output of the amplifier should be kept at half of supply voltage. Let us say you are using a single supply amplifier. Imagine you are using a single supply amplifier like this. Now the output of the amplifier should be half of supply voltage. If this is V, this has to be kept at half of V. Why? Because the amplifier should be at the middle of the load line, right? If the load line's one end is at 0 volts, the other end is at supply voltage, amplifier should be operating at the quiescent region. In the case of BJT, it is called as active region. In the case of MOSFET, it is called as saturation region. That means the switch is supposed to be working at the quiescent point, which is exactly half on and half off. So in such a case, if you are using an amplifier, now you will have to bias this amplifier in such a way that it is at half of the supply voltage. That is why in the BJT circuit, you had studied about fixed bias and self bias and voltage divider bias. You had studied about JFET's biasing also in the same manner. That was the basic requirement of biasing an amplifier. So if you use a single supply, let us say you are using an integrated circuit. For an amplifier, you are using an integrated circuit because op-amp is an integrated circuit. Now, when you use the op-amp with the single supply, you will have to bias the op-amp so that its output will be half of the supply voltage. Now, this is one requirement. Now, let us say we change this. Let us say instead of the ground, let us say instead of the ground, we have this minus V now. Let us say upper one was plus V, lower one was minus V. In this case, there is no need to bias this amplifier now because by default, it is at 0 volts. Output, if it is at 0 volts maintained, so if output is maintained at 0 volts, actually output will be at 0 volts, right? When input is not supplied, output will be at 0 volts. When you have a plus V and minus V, by default it is at 0 volts. So the biasing portion of the amplifier can be absent in this case. That is the advantage of having dual supply. So in our particular experiment, whatever we are dealing with now, we have this dual supply. That means we have minus 2.5 and plus 2.5. If at all we used 0 volts in the case of VSS, then we would have to bias this NMOS separately by keeping the V out at half of the supply voltage. That requirement is not there now. That is because we are using VDD and VSS. That is the advantage of using dual power supply. Apart from that, do you find any other differences? Obviously, the next difference is this Pmos. Now let me write one more circuit here. Okay. Now, you are seeing a circuit at the right side. I had already shown you a resistance at the drain, which is required. Now, the output coupling capacitance we are leaving out in this case because we are only measuring the direct output here. If you want later on, if you want to couple this amplifier to the next stage, we can always put a coupling capacitance there. That is no problem. Coupling capacitance is required here anyhow at the output. Now compare the circuit at the right side with the left side. There is this VSS and there is this VDD. So in general, this will be at 0 volts, we can say. We don't have to bias this NMOS separately because the source we have kept at minus 2.5 and the supply voltage is plus 2.5. That way, input we can directly give here at the gate without the DC blocking capacitance. Now, if I say that this RD we are replacing with this Pmos, my question now to you is two questions. First question is, if I replace this RD with this Pmos, what is the advantage? One question. Second question, is it possible to replace this resistance with the Pmos? Let us make the second question as the first question now. Is it possible to replace the resistance with the Pmos? How can a Pmos work like a resistor? Any answer? Any answer? How can this P Mosfet work like a resistor? Okay, Kuldeep is giving the answer. I guess in ohmic region it acts as a variable resistor. It is not your guess, it is correct, but it is not a variable resistor. In the ohmic region, it is a fixed resistor. In the sense, let me write the characteristic curve of MOSFET. You know it is like this, right? Now in this region, this is the linear region. In this region, its resistance is constant. But this is based on a particular VGS value, right? Based on a particular VGS, you can have different curves. Let me write one more curve. You can have a different curve like this, right? So like this. So when you have different curves, based on a particular VGS, its slope is going to change. But in this region, wherever is the ohmic region or the linear region, it is called as ohmic because it is working like ohms. It is a resistor only. Now we fix a particular VGS such that we want a particular value of resistance. For obtaining a particular value of resistance, we can fix a value of VGS and we can fix this Y by X. That Y by X is nothing, sorry, X by Y. X axis is voltage, Y axis is current. So X by Y is nothing but the resistance. So we can replace this resistor with the PMOS device by giving a V bias. You are seeing a V bias there. That V bias is basically VGS. So for a given VGS, we can fix the resistance of the transistor. So for the one question, the answer is resistor can be replaced with the transistor when the transistor is operating in the linear region or in the ohmic region by applying a requisite gate to source voltage. That is where we keep on telling MOSFET is a voltage control device. By means of a voltage, we can control its switching operations. This is the first question. Now the second question is, what is the advantage of replacing resistor with PMOS? Can anybody tell me what is the advantage of replacing the resistor with the PMOS?
So does it have something to do with pull up, pull down?
Right now, this is a pull-up transistor only, right? Pull-up in the sense you will have a resistor at the top, that is called pull-up. If you have a resistor at the bottom, it is called pull-down. Now, in this case, the bottom transistor is the amplifying transistor. And the upper transistor is the one which is being replaced for the resistor. So, it has to be pull-up only. That is not the exact answer. My question is, what is the advantage of replacing a resistor with a transistor?
We can vary the value of RD with respect to
Okay.
our needs.
Yeah. You mean to say when we apply biasing voltage, we can have different values of resistance. But that is possible here with the RD as well, right? We can as well replace the RD itself directly. We can have a variable resistor in both the cases. Harshita has given the answer. Changes in VGS directly change the value of the resistor. That is fine. Changes in VGS changes the value. That is why we are using a V bias at the left side so as to get a desired value of resistor. But that way here again, when we directly put a resistor also, we can put a desired value directly. That is not the advantage. That is the regular concept as it is. My question is, what is the advantage if we replace resistor with the MOSFET? Why are we doing this? Because if at all we replace the MOSFET, we need one more biasing voltage. We can directly connect the resistor itself, no? Instead of connecting a resistor, why are we connecting a transistor? And we have a complication of putting again a bias voltage. Can anybody tell any other answer? Kuldeep says it is related to manufacturing. In what way? Yeah, it is related to manufacturing only to some extent. But exactly what? Okay. He has given the hint, but he has not given the complete answer also.
Equal number of NMOS and PMOS are to be maintained or something like that.
No, no, no. No, no, no. It has nothing to do with that. Kuldeep says Cmos consumes less power. No, that also is not the answer. Because when we fix the value of the resistance, now Pmos is replaced with the resistor, that's all. That ohmic drop across the transistor also will be there. It is V equals I into R, which is going to be applicable in both the cases. Instead of the physical resistor, we are connecting the Pmos as the resistor. But now Pmos is also working like a resistor only. So that way power consumption will be there. Or ohmic loss will be there across the resistor because there is a drain current flowing. That is not the answer. But you are nearer somewhere. Okay, let me tell the answer. But before telling the answer, let me erase this, whatever I have written here. Because I want the circuit to be remaining there. Okay. Now you can see, we know that R is equal to rho into L by A. So if you need a 1 kilo ohms resistance here, let us say you need a 1 kilo ohms resistance. Now, if you need a 1 kilo ohms resistance, area of cross section must be lesser, length must be more, because the resistance value is inversely proportional to the area and is directly proportional to the length. Now think about the integrated circuit. Don't think about our regular lab experiments where we are using physical resistors. Inside the integrated circuits, how are we going to have resistor? Of course, in the discrete lab, we have a physically manufactured resistor that we are going to connect to our circuit. But in the integrated circuit inside the chip, how are we going to have a resistor? We have many materials inside the chip. We have P substrate, then we have N-well, then we have polysilicon, then we have implantation or diffusion, then we have metal, we have oxide. In these many layers, oxide is insulator, but polysilicon is not a very good conductor. It is not a very bad conductor also. Polysilicon is somewhat a conductor. But we have N well, again that is a conductor only. P sub, that is also a conductor only in one way or the other. Metal is now a very good conductor. So we should use those materials only for manufacturing resistors also, for manufacturing capacitors also inside the chip. Please remember that. We are thinking about the chips inside, not chips outside. If it is chips outside, we can easily connect a physical resistor. Now we are discussing about the inside, where area is costly, area is expensive. More the area consumed by a component inside the chip, it is going to become expensive, because in the VLSI manufacturing, area equals cost. If you can pack 1 lakh transistors in a digital circuit, now if someone else is going to pack 10 lakh transistors or 2 lakh transistors in the same area, naturally he is going to save cost there. So in such a case, whenever we go for manufacturing of the integrated circuits, basically MOSFET is for VLSI. Now, if we directly have to have a physical resistor there inside the chip, we will have to reserve this much of length proportional to 1 kilo ohms, and cross section must be lesser, length must be larger. That means, let me write it below. You should have such area reserved. You will have such area reserved. Now, L, length is there. Area of cross section, A is there. Rho is the resistivity of the material. Whether you use it as a N implant or a P sub or whichever particular layer is selected for manufacturing resistor. Now, outside the chip, you have discrete resistors. They are made up of carbon films or metal films, which are coated on a ceramic substrate. But that is impossible inside a chip. Inside the chip, we are dealing with micrometer and nanometer dimensions. Whereas outside the chip, when we have discrete resistors, we are dealing with millimeter and centimeter dimensions. So, whenever such constraints are there, the IC manufacturers, what they do is, if at all there is a larger value of capacitor required inside the chip, they cannot have a larger value capacitor. You cannot have a 1 microfarad capacitor inside the chip. For that matter, manufacturing a nanofarad capacitor inside the chip is also expensive, area wise, because you know that C is equal to epsilon A by D, where value of capacitance is directly proportional to the area. So in general, inside the chip, if capacitors are required, it may be in general femtofarad or attofarad, at the most picofarad, not even nanofarad. Forget about microfarad. So if a chip requires a microfarad capacitance, they will simply bring the pin outside the chip, and you will have to physically connect to an electrolytic capacitor outside the chip. That is what is the approach. Now that is about capacitance. Same thing about resistance. Let us say if a resistance is consuming a larger area, let us say they need a 1 mega ohms resistance or 2 mega ohms resistance. Now that mega ohms resistance may not be possible to implement even using a MOSFET. Now in such a case, they will bring the pin outside and they will ask us to connect a physical discrete 2 mega ohms resistance outside the chip. But now we are thinking about common source amplifier, which is inside the chip. And in our case, the resistance will not be in the range of mega ohms. So we can simply replace the resistor with the MOSFET, because the MOSFET works like a resistor in the linear region. That is the point here finally. Finally, instead of wasting this much of area, which I have shown you below, instead of wasting this much of area for a resistor, simply use a MOSFET, because MOSFET is simply a source and a drain and a gate. That's all. MOSFET will be much smaller than the resistor in this case. Please remember that. In general, people think transistors are having a larger area than the passive devices. That is the case with the discrete devices. In the discrete devices, you are seeing a resistor which is small, a ceramic capacitor which is small, and you are seeing a transistor which is bigger. The transistor is made bigger that way purposefully so that we can handle it. Otherwise, inside the transistor, it is a small silicon chip again. Only power transistors are made much larger size because they have to handle large amount of current. They have to handle large amount of power. But power transistors are not possible even inside the chip. If at all a large amount of current or power has to be handled by a transistor, we cannot integrate it as a silicon chip in VLSI. We will have to have a larger transistor only. That's why you could have seen in the labs, the power transistor mounted behind the power supplies. You would have seen that big transistor called 2N3055 that is mounted behind the power supply, so that when it is mounted behind, the heat which is there with the transistor will be easily dissipated to the atmosphere as well. So the life of the transistor is going to be increased. Of course, the transistor also will be having the heat sink also with it. So we are not discussing of those devices which are going to be of bigger size. We are discussing of those devices which can be implemented inside the chip with the smaller area. So the answer to this question is resistor is replaced with the Pmos just to save the area, nothing else. Now, I have told you all the basics now. Why we need V bias, I have told. Why we are replacing resistor with the P Mosfet, I have told. Now the last question is, why P Mosfet? Why not N Mosfet? Because N Mos also works in the linear region, right? Why don't we connect one N Mosfet here? Why are we connecting a P Mosfet here? Any answer? Nobody is answering. Okay, Kuldeep says mobility is less. Partly, but it is not actually the mobility. Partly you are right. Large resistance can be achieved. Yeah, that is right. Large resistance can be achieved by applying that VGS accordingly. That is right. But that is again not really the very accurate answer. The answer is, you already know that Pmos passes good 1 and Nmos passes good 0, right? So whenever we connect at the top, we prefer Pmos because it passes good 1. And if at all it has to be utilized below, we use Nmos. In the next experiment, we are going to use Nmos only. Because in the next experiment, we are going to deal with common drain amplifier. I will discuss that only in the next class, not today. So here, because we are connecting VDD at the top and we need resistor at the top, we are replacing resistor with the Pmos only, because Pmos passes good 1. If it is the other case, let us say the amplifying transistor is at the top and the resistor is supposed to be at the bottom, just like our emitter follower circuit, then we can use Nmos also there. That is the answer. It is not about mobility, it is not about large resistance. Okay. Now you can see these dimensions here. Nmos is having a length 1 micrometer and width 20 micrometer. Pmos is having a length 1 micrometer and width 50 micrometer. Now the width of the Pmos is much larger. This is related to mobility. Because in general, in the 180 nanometer process, mu n is around 2.3 times mu p. Mobility of electrons is about 2.3 times larger than the mobility of holes. So that way Pmos will be slower compared to Nmos. To compensate that, we increase the width of P Mosfet. So here you can see P Mosfet's width is 50 micrometer. and the NMOS width is 20 micrometer. But in our earlier experiments, we were using the length in nanometer. Here you can see L is 1 micrometer. And we are talking about VLSI only. In VLSI, transistor is supposed to be having a nanometer dimension. Why is that in this amplifier we have 1 micrometer? What can be the answer? We have changed the length of the device also to 1 micrometer. Both the devices have the length 1 micrometer. Width is changed, for which I have already told you the answer in comparison to the Pmos and NMOS width. But why length is in micrometer? The answer is, now this is an amplifier, right? Yeah, Kuldeep has given the correct answer. Now it is an amplifier. When it is an amplifier, it is going to handle current in milliamperes. You already know the equation, right? Equation for drain current. IDS equals, sorry, I'll have to, writing with the mouse is difficult this way. IDS equals, or let me write, IDS is proportional to W by L. IDS is equal to mu n into Cox into W by L into Vgs minus Vt whole square by 2 in the saturation region, right? So the drain current is proportional to width. It is inversely proportional to length. So we have made it proportional to width. That is why width is much larger. 20 micrometer and 50 micrometer, width is much larger. But length proportionately has to be larger. Otherwise, if the channel length is nanometer, let us say the width is 20 micro, 50 micro, MOSFET will burn out. Width and length, it is also called as aspect ratio. Actually, L by W is called as aspect ratio. W by L is the inverse of the or reciprocal of the aspect ratio. Now, length and width have to be proportionately larger in this case because it is going to handle a larger amount of power. If we keep only the width larger and if we keep the length smaller, that device may not be able to evenly distribute the power because device is basically an area. So when we increase the width proportionately, we have to increase the length as well, even though current is inversely proportional to length. So that is how we are increasing the length and we are increasing the width also much larger. That is the answer. So when you start simulating this particular circuit, you will have to change the dimensions of NMOS and PMOS to the one that is shown here. Otherwise, the default dimensions of NMOS is 180 nanometer and 2 micrometer. You will have to change it to 1 micrometer and 20 micrometer. Accordingly, you will have to change the dimensions of P Mosfet also. Okay, I hope I have covered the complete basics of this experiment now. Let me proceed. Is there anything else which I have to discuss? If students still have any queries, you can ask me. Otherwise, I will proceed now. Okay, Kuldeep says no. That means no questions. Let me proceed. Now, once you pick up this NMOS and PMOS, from the analog lib library, you will have to pick up this VSS symbol and VDD symbol, and you can place these pins. By placing these pins, gradually you can make a symbol for this amplifier. Now, this is a common source amplifier. You can make a symbol. There is a default symbol that is coming. You can use the default symbol also, or you can make a symbol like this. Now, this is the symbol for the regular amplifier. You can create a symbol also, or you can use the default symbol also. That is your choice. Now, after making a symbol, now you already know that AC analysis is for plotting the frequency response and obtaining the gain. And DC analysis is for checking the transfer curve, and the transient analysis is for verifying the shape of the output waveform. So that way, we will have to set the AC magnitude as 1 millivolt for obtaining AC response. The amplitude 5 millivolts is for checking the waveform shape in the transient analysis. It is not mandatory that you have to keep it at 5 millivolt also. You can keep this also as 1 millivolts. It doesn't matter. Here I had made it as 5 millivolts so that the waveform will be much larger. In amplitude, we can easily observe it. And the frequency is 1 kilohertz, which we choose here. You should not enter the units. That means hertz or voltage you should not enter. The tool automatically takes it. Now, for the V bias, keep the DC voltage as minus 0.9 volts. Now, why minus 0.9 volts? That I cannot discuss now because there is a lengthy theoretical discussion. You are going to learn about it only in the next semester. You already know that the gate to source voltage is going to control the conduction of the transistor. Now, VDD and VSS are 2.5 volts and minus 2.5 volts respectively, which you can set by selecting an instance called VDC from the analog library. Now you have to connect like this. Finally, you will have a circuit like this. You will have a common source amplifier. It is named as CS ampere. The default symbol is utilized and the V bias is here. That VDC is minus 900 millivolts or minus 0.9 volts. That is the biasing voltage. Then you have this regular input signal, which is a sine wave. You can see here, this is V sine, which is taken from analog library, where its amplitude is shown as 5 millivolts and frequency is 1 kilohertz. And you can see the output wire and the output pin. You can also see the VDD symbol here and the ground. In between VDD and ground, there is this VDC, which is plus 2.5. Now again, you can see VSS and ground. This is the VSS symbol, which is always downwards. VSS is connected to this terminal, and you can see this VDC is given as minus 2.5. That means VSS is minus 2.5 with respect to ground, with respect to 0 volts. And VDD is plus 2.5 with respect to ground. Anyhow, VDD and VSS symbols we had given inside the amplifier circuitry, and the tool will relate those symbols and it will automatically apply plus 2.5 and minus 2.5 to the amplifier circuit. That is what is the meaning here when we give the power supply sources. Now my last question is, when we give this gate to source voltage as minus 0.9, what is VGS? I will come back to this circuit now. We have given the gate to source voltage V bias as minus 0.9. This is now minus 0.9. And this is now 2.5. This is minus 2.5. And then you will have a input signal here and you will have a output signal here. Now this Pmos is working like a resistor itself. So my question here is now, to the gate we have given minus 0.9. To the source we have given 2.5. What is VGSP? Can anybody tell me? VGSP is how much? Can anybody tell me what is VGSP? There are 11 students. Are they all listening? I get response either from Harshita or from Kuldeep or from Vanilla. Other students are totally passive. Any answer? What is the value of VGS? Harshita has given the answer, minus 3.4. Very good. It is correct. VGS, gate to source. Source is at plus 2.5. See, source is at plus 2.5. And gate is at minus 0.9. Now, when you have to move from gate to source, minus 0.9 minus of plus 2.5. So, it is minus 3.4 volts. Very good that Harshita has given the answer. It is minus 3.4 volts. So, you know that Pmos is going to work in negative gate to source voltages. Now, when we are giving minus 3.4 volts, that is the voltage which you chose to keep the Pmos in linear region or in ohmic region. That way, VGS is related to the conduction of the MOSFET. That is why purposefully minus 0.9 is chosen. That is the basic that is sufficient for this semester. In the next semester, you can explore more about the relationships of voltages with the conduction of the transistor in the analog domain. Now coming back, you have this symbol and you have connected all the power supplies, inputs, and what you can do is directly go into the ADE, analog design environment, and you can set all the parameters. So in the ADE, for transient, for DC, for AC, you can set all these. You can start, you can have the sweeping range for the frequency from 100 Hertz till 1 gigahertz. That is what is seen here. Actually, you can give much more also. You can give 1 tera, 1 peta, 1 exa, 1 zeta, 1 iota. Like Rajnikant says in the film Robo. Robo, I think you have seen 2.2 also. Memory, 1 zettabyte. Speed, 1 terahertz. That way. Speed you can give more than 1 tera also. A cadence will take much larger multipliers as well. But here we are choosing 100 to 1 gigahertz for this particular amplifier. Now we set that frequency and we set the points per decade as 20 dB per decade because we want to have a gain and phase response curve also later on. So then when you simulate, you are seeing this curve. Let me slightly zoom out. Now you are seeing this curve. You can see the transient response here, where you can see the input signal and the output signal are 180 degree out of phase, which is supposed to be so in the case of a common source amplifier, because common source amplifier is same as the common emitter amplifier with BJT. So there is a 180 degree phase shift, and you can observe the waveform at the output. That is also almost a sine wave only. The wave shape is retained. There is no amplitude distortion in the output. That is why we perform transient analysis to check whether the waveform is having a distortion or not. There is no distortion and there is a 180 degree phase shift. Now you can see the rightmost curve. In the rightmost curve, this is DC analysis. When the input is rising up, just a minute, I am muting. Okay, now to continue with the class, you can see the rightmost diagram where you can see the DC analysis where we have set the input from minus 2.5 to plus 2.5 DC at the input. Now you can see at the output it is, initially it was plus 2.5 gradually going down and it is remaining here. It is gradually going down, which means you can understand that the amplifier is going to give a 180-degree phase shift. When the input was here, output was here. When the input is rising, output is falling in the DC parameters. So we can immediately come to know this is an inverting amplifier. Now my question is, again, you may keep saying, sir, how many questions you are going to ask? I am going to ask questions only to clarify. Okay. Whenever I ask you questions, it does not mean that you will have to give the right answer always. I will be giving you the right answer later on. But if I don't ask you any question, then I don't have any interaction at all. I feel as if I am talking to a laptop only. I always want interaction with the students, whether students like it or not. Without any interaction with the students, I cannot have a one-sided teaching at all. That is why I keep asking questions now. Now the next question is, it has stopped here, but whereas in the case of inverter, it had gone down till here, right? In the inverter we had seen it will go down till bottom also. But in the case of our common source amplifier, it has stopped here. The question is why? Can anybody answer? It has stopped somewhere at minus 1.2 volts. It was supposed to go to minus 2.5 volts. Because it is from minus 2.5 to plus 2.5. If it is given a complete 180 degree, it should work like an inverter only, right? It has to go from plus 2.5 to minus 2.5. But it has stayed here at around minus 1.2. What is the answer? For inverter, Pmos is connected to ground. Yeah, that is fine. But in the case of this amplifier, it is connected to minus 2.5, no? It has to go till minus 2.5, right? Because this is also an inverting amplifier only. Basically, inverter is also an amplifier. Only thing is, we use inverter in two states. Otherwise, to the same inverter, if you give a small sine wave at the gate, that is also going to amplify to some extent. Ultimately, amplification is nothing but switching only, right? Switching between lowest state to the highest state. That's all. So my question is, now this is also an inverting amplifier. It is going to give 180 degree phase shift. But why in the DC analysis it is not going up to minus 2.5? It was supposed to go there. Any other answer? I appreciate you for your effort in answering. But that is not the exact answer. Any other answer? Okay, the answer is, yeah, here EE gets amplified output, we get amplified output, that is fine. See, amplifier is basically a switch only, transistor is basically a switch. We use the switch at the midpoint, then we call it as an amplifier. We use the switch with the two low point and high point, lowest point and highest point, then we call it as a logic gate or an inverter. Otherwise, transistor is basically a stupid switch. We intelligent people are using it as per our application. Amplifier does not know whether it is analog or digital at all. We are using it as analog and digital based on our requirements, based on its functionality. So that way, your answer is correct. It is amplified output only, but my question is not that. My question is, it is supposed to go till minus 2.5. Why is it not going? The answer is, let me show you the circuit once again. The answer is, let me zoom in. Let me annotate. We are using this as a resistor, right? We are using P Mosfet as a resistor. Now, when we increase this from minus 2.5 to plus 2.5, gradually this is a resistor, and gradually we expect the NMOS to completely turn on, right? If NMOS completely turns on, let us say this is like a switch. And let us say if this switch is closed now, let us say NMOS is closed now. Now this point, this particular point gets connected to minus 2.5. We are taking output here, right? Now my point was output remains here at minus 1.2. It does not go till, it does not go here. It does not go till minus 2.5 because this NMOS completely does not go into linear region. NMOS also works like a resistor at that time. If NMOS completely turns on, then only we will get minus 2.5 here because this is connected to this. But it does not happen that way. It does not happen that way because this is not an inverter. In the inverter, we did not bother about any of these things. We used to operate it only in the two regions, in the linear region and in the cutoff region. But in the amplifier, this is supposed to be at the saturation region. It should neither be completely on nor should be completely off. If this NMOS becomes completely on, then we have an amplitude distortion. Let me show you that. Now, we have an input here. We expect an output like this, right? We expect an output. Now, the output is supposed to be between minus 2.5 and plus 2.5. Now, if at all there has to be a faithful amplification, this NMOS should not go into deep linear region or deep threshold region at all. It should not. That is called, what is that? Deep threshold, sub-threshold, whatever. What do we call? When the transistor goes into the full linear operation, in the curve we have a name for this particular area. Later on it is like this, but this particular area, what is it called? Deep triode region. It is called deep triode region. In the case of an amplifier, it should not go into deep triode region. In the case of an inverter, it can go. In the case of an amplifier, the switch which we are using should not go into deep triode. If it goes into deep triode, we will have amplitude distortion. In the sense, if the transistor goes into deeper saturation, if the input signal increases by its amplitude, let us say, if the input signal increases by amplitude, instead of a sine wave, you will have a square wave, right? Now that is an amplitude distortion. The amplifier is supposed to be a faithful amplifier. It should not give a waveform's amplitude distortion. But that happens if the input signal slightly rises, it may go into deeper triode region. Now, to prevent that, the N Mosfet should never be going into deep triode region. So the thing here is, as this is going to work like a resistor, this also will come into a linear region which will remain like a resistor. Now you will have a voltage divider network with when the input signal is rising fully, even this NMOS will work like a resistor only. It will not absolutely close like a switch. That is how these dimensions are again decided. This W by L is again have a relationship there. I cannot tell you the more details about it because it is meant for your theory class only. But all these device dimensions have the relationships with the functionality of the switch. In that way, now this is working like a voltage divider network where this will never go to minus 2.5 because there is a resistor here. That is the answer. I hope I am going into much larger basic details, but I hope that is my job to go into much larger basic details. Otherwise, if you don't explain all these things, then we hope you are independent. You need not depend on a teacher, right? So even though you think that I am discussing too much of basics, in fact, I have to discuss too much of basics. If students are aspirants, means if students are learners, that is the only intention, nothing else. Otherwise, many times I have got a blame also that I show off a lot. I don't know whether I show off or not. I simply express whatever I know, and as a teacher, that is my job. But many times, even some students have also blamed me that I am showing off, or at times I am arrogant. There are comments on me. Whether I am arrogant or not, I don't know. If I am arrogant, my wife will repair me. Correct. Right. Okay. Husband and wife together are going to correct each other. So if I am arrogant, my wife will take care of it. Others need not bother. Okay. But I should say that I am confident. I may not be arrogant as such. I feel so about myself. But I am confident at times. I can be tough at some times. Okay. When it comes to such principles. I follow my own such principles because I feel as educated and evolved human beings, we have to live a better life. That has been my effort. So when we live a better life, we should be better in our profession also. We should teach well also. That is why I am discussing all these things. Otherwise, lab class can be completed within half an hour, 45 minutes, right? Why should we have this much of lengthy discussion for one small circuit diagram? That is what some of my other colleagues also think. They think, why we should give this much of lengthy explanation for a small 2-transistor circuit? We have to finish it within half an hour or 1 hour. Sometimes they also think, why should we have a theoretical explanation in the lab at all? Whatever is related to lab, only that we have to discuss. Why all these theoretical things we have to discuss in the lab? Now the point is, if we don't discuss, then how do we enrich the knowledge of the students? That is the whole point, nothing else. That way I should thank Harshita, Vanilla and Kuldeep that they have been continuously interacting with me. Only when you interact with me, I feel happy that this discussion is reaching my students. If the other students also are active listeners, that is enough. You don't have to keep on interacting with me, but if you are actively listening and if you are trying to understand the basics, that is enough. Otherwise, after 4 years BE, what have you remembered? You will have to question yourself. After finishing 4 years of engineering education, ultimately what you carry in your memory, that is going to make you proud to feel that you have finished engineering. Otherwise, many of my students may get into business. Some of my students may get a good dowry also, we don't know, after finishing engineering, right? But if you want to feel that you are proud to be an electronics engineer, you should be thorough with all the basics. So with this sermon or with this unnecessary discussion, let me continue the necessary discussion now. We have seen the transient analysis and we have seen the DC analysis. Now there is this EAC analysis at the middle, where you can see we have gone for a direct coupled amplifier. That is why you are not seeing a reduction in the gain below here. Otherwise, normally the curve will have something like this also, no? But that is not there here now. Why? Because we have not gone for a coupling capacitors at all. Neither in the input nor in the output, we have not connected any capacitors. At the input, we have used the gate capacitance itself as the input capacitance. But that is a very small capacitance. So because of this, now this particular amplifier is a direct coupled amplifier. Just like an op-amp is a direct coupled amplifier. So in that way, you can see that the bandwidth, you can see directly from 0, there is a gain. There is a 12.5 times gain. That means we gave AC magnitude as 1 millivolt and we have got the output as 12.5 millivolts. That means this amplifier is giving the gain 12.5 times voltage gain. But you can see Later on, after a certain frequency, it is going down. Somewhere after 10 power 8. 10 power 8 means it is around 100 megahertz. After 10 megahertz, 100 megahertz, the gain is going down. Now, this is the gain as well as the frequency response. Here, you will have to move your mouse all the way down 12.5 into 0.707. You will have to multiply that. Then, you will have to move the mouse here. Wherever the mouse is showing that 12.5 into 0.707, there if you keep your mouse, the cadence tool is going to show you the amplitude or the frequency, amplitude, frequency both. Now that frequency is the upper cutoff frequency for this amplifier. That can be taken as the bandwidth. That is one method. There is another method. Let me show you another method. There is in the ADE window, in the pull down window, there is one menu called results. When you click on results and when you click on direct plot, when you click on results, you will get this option called direct plot. When you click on direct plot, there is another option called AC gain and phase. Now, when you click on that, you will have to click on the output wire, okay, and on the input wire together. Click on the output wire first, then input wire next. Automatically, the cadence tool itself will calculate output divided by input, both gain and phase. Now, you can go for that strip chart mode there, then you can come down, you will see this particular curve on the screen. Now, you can see the lower one is the gain curve, upper one is the phase curve. You can see upper one phase curve, there is this 180 there, and lower one is the gain curve. You can see 12.5 times when it is converted into decibels, it is now 22 dB, approximately 22 dB. Let me zoom out so you can see it clearly. You can see that now. This is now around 22 dB. And you can see the phase, it is 180 degree. That means it is a inverting amplifier. Amplifier is producing 180 degree phase shift, common source amplifier. And there is this 22 dB. Now we can. Vanilla wants to ask something?
No, sir.
Okay. Now, you can see that at a frequency of around 10 power 8 afterwards, the gain is going down. Now, you'll have to move your cursor to a point where 22 minus 3. You have to go to a 3 dB cutoff point. 22 minus 3 is 19. So, you have to move this particular point where the mouse will show you, cursor will show you, instead of 22, 19. And there itself, the cadence tool will show you the frequency for that corresponding point. That frequency will be the bandwidth of this particular amplifier. Now, you can see that the amplifier is having somewhere around megahertz only. It is not having gigahertz gain. Its gain is going down. It is having a few megahertz of, bandwidth, megahertz of bandwidth only. Why? MOSFETs have lot of internal parasitic capacitances. It is very difficult to achieve larger bandwidth with MOS amplifiers. It is easy with BJT amplifiers that way. That is why even today BJT has remained, even though MOSFET has come into limelight, majority of the chips are having MOSFETs only inside, but still we have a bi-CMOS technology, we have a bipolar as well as CMOS technology. BJT has still remained. Sometimes I keep joking in the class that just because son-in-law came, son need not go, right? Just because mother-in-law came, mother need not go. Or just because wife came, mother need not go, right? Or just because husband came also, father need not go, isn't it? Same way, BJT was there earlier, BJT will remain now also. Because we had used BJT for many years. Even now we use BJT whenever a high power is required or a high bandwidth is required, because BJT is having lesser parasitic capacitances. It is a current control device. Whereas MOSFET is a voltage control device, it is containing a lot of capacitances inside. Because of which we have bandwidth issues. So it is not really easy to obtain larger bandwidth using MOSFET. Even today, that is a challenge to get a larger gain and larger bandwidth using MOSFETs in an op-amp also. So for that matter, the very popular op-amp 741 is not based on MOSFETs. It is based on BJTs only. It was designed many decades before. Even now it is popular. Even now we use it in the lab experiments. Why? Because it is designed using BJT, not using MOSFET. So you can see the gain response here, gain and the frequency response. You can measure the bandwidth. Now you can see the phase response here. Even the phase has not remained constant. I hope in the EAEC class, the gain margin and phase margin was discussed at length with you people, and I hope you remember those basics. There is something called gain margin and phase margin. Larger the gain margin and larger the phase margin, amplifier is more stable. Any amplifier is supposed to have gain margin and phase margin. If the amplifier is not having gain margin and phase margin, then the amplifier is highly unstable. In the higher frequencies, amplifier may become oscillator there because of the feedback within the amplifier itself. There may not be actual feedback. Otherwise also, amplifier may become completely unstable. There is a Nyquist criterion there. I hope you remember all that. So in this case, we have a phase response at the top and we have a gain response at the bottom. And you can see that even the phase is going down. It was supposed to be 180 degree. But beyond certain frequencies, because of the parasitic capacitances which are inside the device will not work in an ideal manner at higher frequencies. Because of the non-idealities, now phase is also coming down. What is gain margin and phase margin? Whenever the phase is becoming 0, gain should not become 0 dB. Or whenever the gain is becoming 0 dB, phase should not become 0. That is the idea there. If they become 0 at once, 0 dB corresponds to unity gain, right? If output is equal to input, gain is reducing. Now, when the gain is reducing, when the output equals input, then the gain is unity. When the gain is unity, in decibels, the gain is 0 dB. So the Nyquist criterion says, this was invented by Nyquist himself. That says that in the complex plane, 0 dB and 0 degree should not coincide. That is how gain margin and phase margin are defined. Now you can see here. Actually, you can simulate this experiment to a larger frequency also, and you can verify whether the amplifier is having a gain margin and phase margin. You can actually measure the gain margin and phase margin also. I am unable to show you in this particular snapshot, but whenever you come to the offline lab classes, when you have time, you can try out all these things. If not this semester, if you remember all these basics, even in the next semester, you can try out all these things. If you feel passionate about VLSI designs, then you can spend your free time in the VLSI lab itself. You can conduct many other experiments. I have been advising you or suggesting you in whichever way you take it. And you can take some of these designs for your mini project in the next semester. And there you can observe all these things further. In fact, for a mini project, you can choose one op-amp itself as a new design. You are learning new design, op-amp design in this lab itself now, in this semester itself. You can design your own op-amp in a different way. And that can be your mini project. There you can measure the gain margin, phase margin also. Okay. With that, I am coming to the end of today's class. The layout of common source amplifier and the circuit description of common drain amplifier and the layout of common drain amplifier. These things I am going to discuss in the next lab class. It's already nearer to 9:45 now. So let me stop the discussions now, but the meeting will be on. We have been instructed to conduct this lab class for the full time. Full time means it is 3 hours. We may not go till 3 hours, but the meeting will be on. And I think Deepak has already created an assignment in the Google class.
Yes.
Deepak, have you created?
Yes, sir, I have created, sir.
Yeah. So Deepak has created the assignment in the Google class. Students have to write the observation book now. Students have to write the observation book in the sense of observation page. Whatever you learned in today's class, write it as the observation page and convert it into PDF and upload into the Google class. After uploading, students can leave this meeting. Whoever uploads the observation book for today, you can leave the meeting. Until then, meeting will be on. I will not be closing the meeting, but I will be stopping the recorder because the recorder will be simply moving. It will be of no use if it is remaining blank. So I will be stopping the recorder. Before that, if students have any other questions, you can ask me. I will wait for 1 minute now. Okay, if there are no questions, I'll stop the recorder and I'll mute myself.